Okay, this lecture is over Module 5 of your curriculum entitled Number Systems. So we'll start over here with 501, which is an introduction, which is always, why should I take this module? The purpose of this is to teach you about number systems that are used in networking as well as programming, computer science, other than base 10, which of course is what we normally work in. Hopefully before watching this Module 5 video, you watched my first supplemental video that I did on number systems that will give you some background, some of which will be repeated here, some which may not. But talking about number systems, one of the first number systems that we talk about in networking and computers is base 2 or binary. And there's several things here that you need to know that we've discussed before. The first is an IP version 4 address is 32 bits in length. So this big long 32-bit number right here would possibly be an IP address. I don't really think they should have put the periods in there just yet. But what happens is, since that's a pretty long number to repeat to somebody or to memorize, what we do is we take 4 bytes. 4 times 8 is 32. So that's what they've done here with the period, is they're showing you where those byte boundaries are. Then within each byte, they convert that to the decimal equivalent, put periods between it, and call it decimal dotted notation. So this big long IP address, we would be more likely to say 192.168.10.10 is the IP address. If we talk about IP version 6 addresses, we haven't talked about why we have IP version 6 yet, I don't think. But an IP version 6 IP address is 128 bits, so 4 times as long. And that doesn't mean we have 4 times as many. We exponentially have more IP addresses in IP version 6 than the 4.1 billion approximately that we have with IP version 4. To make this more manageable, the decimal dotted notation would be quite long. We actually use hexadecimal or base 16 to represent IP version 6 addresses. So as a network administrator, you will need to be able to understand these number systems, be able to convert from binary to decimal, binary to hexadecimal, etc. So that's the purpose of this module. So some of the things that you'll learn here, they only list 2 things. You'll learn the binary number system, and you'll learn hexadecimal, base 16. There may be some other facts, like we talked quite a bit in the intro about IP version 4 and IP version 6. In binary, again, ones and zeros, an IP version 4 address is 32 bits. When I teach this class in person, there's lots of times I go, how long's a MAC address? How many bits are an IP version 4 address? How many bits are an IP version 6 address? What are the 3 pieces of information that a device needs to have configured correctly to communicate on the internet, capital I? So I'm constantly asking that to make sure the students can rattle that off. So what we have here is a network topology. They're showing IP version 4 addresses for the PCs that are in this. They're also showing the addresses of the router interfaces. So this is gig 000 and gig 001 on this router. And then there's a host out here that has an IP address 32 bits. Again, for ease, what we do is we convert these to decimal dotted notation, which I've already explained. And if we do that for all the IP addresses, here we have the 192.168.10.0 network. It has host 10.10 and an interface on the router 10.1. Over here we have the 192.168.11.0 network. Within that network we have 11.1 on the router interface, 11.10 on this PC, And up here we have 209.168.200.225. One thing that I want to mention is a lot of times they will use .1 for the router interface, so it'll be whatever network you're on, and then the host ID or the host number, host address will be 1. Lots of people do that. UK does that. Many people do that. It's just easiest to know that the .1 address on the network is the router, which is the default gateway for that network as well. Does not have to be that. I know AT&T, if they give you fixed internet, they actually use .1.254, the last address, as the interface of the wireless router they provide you with. .512 is a video about converting between binary and decimal. Like I said, I've already put out and hope you've watched a supplemental video on this. This video is about 8 minutes and 21 seconds long, so it's a little long for me to play here. So you can watch that on your own outside class if you need to. 513 is talking about positional notation. This is basically, in my video I called it weights, but position value is accurate too. In base 10, we have 10 to the 0, which is 1. The next value is 10 to the 1, which is 10, 10 squared, which is 100, 10 cubed, which is 1,000. If we keep going, 10,000, 100,000s, etc. So that basically means each position where we have a digit, in this case in base 10, it has a weight. So down here, kind of like my y is 123, 123, they have 1, 2, 3, and 4. There are 4 1s, 3 10s, 2 100s, 1,000, and if we add all those together, we get 1,234. If we're doing this in binary, what we do is we still have the position values 0 through, and often we only go to 7, because there are 8 bits in a byte. So if we start at 0 and go to 7, that's all 8 bits. So the important thing to remember is we're raising the base we're working in, base 2, to those positional values. So 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. And basically once we get to this point, you can still calculate the powers, but 2 to the third is 2 to the 2 times 2. So we can go 4 times 2 is 8, 8 times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. So whichever way makes the most sense to you. So down here they have an example, basically 1 1 0 0 0 0 0 0. What is that in base 10? So we have 128, 164, and then 0 of all the remaining ones. So if we add that together, we get 192. So that's showing you the calculation in base 2. 514 is a check your understanding on the binary number system. You can do that on your own. 515 again is talking about converting binary to decimal. In this case, we're doing the decimal dotted notation, so we're actually doing the binary to decimal calculation 4 times. So our first byte is the same as what we saw before, 1 1 followed by 6 zeros. If we convert that to decimal, we get 192. So that first octet is 192. If we move to the second octet, which is 10101000, and we go through and we apply the weights or the positional values, we have 128, 132, and 18. All the rest of these are 0. If we add all these values up, we get 168. The third octet, or the third byte, I think I mentioned this before, but octet meaning 8, or byte means 8 bits. So here we have 00001011. If we do this calculation, we have 8 plus 2 plus 1, which is 11. And then finally, the last octet we calculate here, we get a value of 10. So it's kind of weird that they put this part up here, but after calculating the 10, in decimal dotted notation, the IP address of that 32-bit number we started with would be 192.168.11.10. Here's an activity on binary to decimal conversions. You can do that on your own. Basically what happens is you're going through, in this case, everything in the table has been calculated. You need to figure out, in this case, we would have 8 plus 2 is 10. So we would go up here and say the value is 10 and then check it. If you want a new binary number, you hit new number, it gives you a new binary number. So like I said, you can do that on your own several times to make sure you feel comfortable with it. 517 is decimal to binary conversion. What I showed you in my supplemental lecture is what I call the division method. You divide by the base you're going to over and over again until you get to 0. You take the remainders of the integer division and write them in reverse order. What they're showing you here is the subtraction method, which I will talk about. And if this makes more sense to you, fine. If the division makes more sense or is easier, that's fine. Use whatever makes sense. So what they have here is they have a representation of the weights for an 8-bit byte. And what you're going to do is you're going to convert the number. And they kind of have a flow chart here. There's going to be an example in the next section. But basically you say, from the number I'm converting, the decimal number, can I subtract 128? If the answer is yes, I will put a 1 in the 128 position, and then I will actually subtract 128 from the number I'm converting. I will take the result of that subtraction and then say, can I subtract 64 from this value? Let's say in this case we cannot, so we would put a 0 in this value. Keep the same number and say, okay, from that number, can I subtract 132? So we're basically going through bit by bit and putting a 1 or 0 there. And if we put a 1 there, then actually doing a subtraction until we get down to the last bit. And the value is either going to be 1 or 0. Can I subtract a 1 from it? If yes, put a 1 here. If no, put a 0 in the 1's position. So here is an example. We have a IP address which presumably we want to convert to binary. So we're looking at the first octet, and then we say they're asking is 192 greater than or equal to 28, which is basically the same question I'm asking. Can I subtract 128 from 192? And the answer is yes. So it says add 1. It's really place 1 in the 128 position. Then subtract 128 from the value, so I have 64. So then, if I move on, here I'm saying, can I subtract 64 from 64? And the answer is yes. So I put a 1 there. I subtract the 64 that's represented by that 1 from my current number, which is 64, and then I get 0. And at this point, it should be pretty obvious that we just put zeros in the rest of the locations. But can I subtract 132? No. Can I subtract 16? No. Can I subtract 8? No. Can I subtract 4? No. Can I subtract 2? No. Can I subtract 1 from 0? No. So the first octet becomes 1 1 followed by 6 zeros. If I continue on through the figure, we look at the next octet. The next octet's value is, in the decimal dotted notation, is 168. Can I subtract 128 from 68? Yes, I can. So put a 1 in that position. Do the subtraction. I have 40. Can I subtract 64 from 40? No, I cannot. So I put a 0 here. I move on. Can I subtract 32 from 40? The answer is yes. So I put a 1 in the 32 weight position. Do the subtraction, and I get 8. Can I subtract 16 from 8? No, I cannot. Can I subtract 1 from 8? Yes, I can. So I put a 1 in the 8's position. And then the rest of these are going to be 0 because 8 minus 8 is 0. So that fills out the octet. If we go through and do this, they're kind of just jumping on. This is 0, 0, 0, 0, 1, 0, 1 because that was 10. That's the value of 10. And then 1, 0, 1, 1 is the value of 11. So the last two, they kind of leave it to you to think through or do on your own. As far as decimal to binary conversion, what they're going to do is give you a 75, and you're going to go through and say, can I subtract 128 from that? No, I can't. Can I subtract 64 from that? Yes, I can. So you can go through and do that activity and then check. It also gives you opportunity for a new number if you like. Okay. This binary activity game, I'm going to try to show it to you here. It's going to open up a new browser and some different things and possibly require me to log in. This is one of my favorite activities. It's kind of been redone a couple of times over the last 15 years. So what happens is you're going to have numbers that kind of build, not exactly like Tetris, but it's going to build from the bottom towards the top. And as you calculate binary numbers from decimal or decimal numbers from binary, or correct incorrect binary values, I think is one of the options too, where they say this binary value equals this number, it's false. You have to set the bits correctly. And if you clear the board or clear a certain number, it used to be if you got 5 right, you won. If you got 5 wrong, you lost. So what I'm going to do is attempt to play this by clicking on the game link. And it's going to open up the browser. It's going to tell me I need to log in to play the game. So I click on that. It's going to have me log into the same account I log into NetAcad. It actually did it automatically for me. It remembered that. So that may be a browser thing. It may be a Cisco Academy thing. But now it's changed to play the binary game. Now, if I click on this, you can read the instructions, but I'm just going to play the game. So here is one that's basically saying, what does this equal? Well, that's 0. So I put a 0 in there and check it. Then it's saying, does this equal 254? No, it doesn't. I need to flip the bits, all the bits at that one, and it goes away. Does this equal 4? No, it doesn't. This one equals 4. Is this 130? So that should be 128 plus 2. What does this equal? So this is the 1s, the 2s, 4, 8, 16, 32. So that should be 32. And then I can clear it. So you can go through. There's a pause button if you need to pause it. Kind of blanks the screen so you don't cheat. But anyway, I'm going to resume this and end the game. And then hope I can get back to the curriculum here. Okay, so that wasn't too bad in the video. So it's kind of fun to play. I recommend you try it out to test your knowledge. Okay, in 5.1.11, we're going back talking a little bit about IP version 4 addresses. I've already talked about that a little. So basically, I'm going to do this in the reverse order. That is, we start with a 132-bit address. We then convert each of the octets to base 10. We put periods between those octets, and we end up with a decimal dotted IP address like 192.168.10.10. Okay, so that's base 2. 5.2 talks about the hexadecimal system. I'll talk a little bit about this in general. It's base 16, so based on my supplemental lecture, that means there's 16 digits. Those digits are between 0 and 15. The problem with a digit like 15 is it's really two numbers. So if we see 1, 5 in a hexadecimal number, we don't know if we're talking about a 1 and a 5 or if we're talking about 15. So, of course, each of these have to have a single digit representing them. So over here at the right, we have digits 0 through 9, and if it's a base higher than base 10, then we start adding letters. So in the case of base 16, we would have 10, 11, 12, 13, 14, and 15. In the middle, we have the binary representation of those in hex. It's half a byte, 4 bits, called a nibble. So those 4 bits, 0 through 15, fit very nicely in 4 bits, going from all zeros to all ones. The other nice thing about hexadecimal, if we're actually trying to represent the value of a byte, we can do that very cleanly with 2 hexadecimal digits. In the case of IP version 6, we have 128 bits that we need to represent. So what we do is we take those 128 bits and we represent them as 2 bytes with a colon between them. And in that case, if we have 2 bytes, that's 4 nibbles. So we can go from 0, 0, 0, 0 to F, 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 F. And we have 8 of those. So they're written in hexadecimal. So down here we have a topology, exactly the same. This is the network number, and then in the case of this, we're using :1. So we have a whole bunch of zeros and a 1 at the end to represent this interface. We would have this big IP address, IP version 6 address, followed by a whole bunch of zeros, with the last nibble being 1010 for 10. So all these are how we would represent IP version 6 using hexadecimal numbers. This video on converting between hexadecimal and decimal is about 6 minutes and 34 seconds long. I covered that in the first supplemental lecture, but I recommend that you go back and watch this on your own after this lecture. Okay, decimal to hexadecimal. Basically what we need to do, there are some tricks to this. So basically what they're doing is telling you to convert it to the binary value. Here they're talking about a byte, and then breaking that byte in half, and 1010 is A, and 1000 is 8. So 168 in hexadecimal is A8. I think I will have a probable supplemental lecture that talks about tricks, This is kind of one of the tricks. I'll go through it really quick because, like I said, I think I'll go through it in more detail. But basically, I tell my students I'm going to give them a hexadecimal number that, or let's see what I tell them, a binary number that's going to go all the way across their exam sheet, and I'm going to ask them to convert it to base 10 or base 16. So if they go through and do that, they're going to go through and figure out weights that are in the millions. Then they're going to keep, divide a million something by 16, and then the result of that by 16. And if they actually go through and try to do it with base 10 as an intermediate step, it would take them forever to do that, and it would be unlikely that they would get it correct. But the trick is, if you're going to hexadecimal, you start at the right, because I can take a string and go, I convert this in 5 seconds. And basically, you take the last 4 bytes on the right, convert it to hex. Next 4, convert it to hex, like they're doing here. But then you continue on. The next 4, convert to hex. And you convert a binary string to base 16 really quickly. You can do the same trick with base 8. And the reason that works is because 16 is 2 to the 4th. We're doing 4 bits at a time. In the case of octal, 2 to the 3rd is 8. So we do the same trick, except doing it in groups of 3, always starting at the right. Down here, they're converting hexadecimal to decimal. So what they do is they say, okay, let's take D2 as 2 4-bit binary strings. D is 1101. 2 is 0010. So the important thing in doing this is you have to have these leading zeros here, or you'll get an incorrect value. You then cram them together, and you get that value. And then they're saying convert that to decimal, so it would be 210. Of course, I've shown you how to go straight from hexadecimal or any arbitrary base to base 10. It's not really that difficult. 525 is a check your understanding on the base 16 number system. You can do that on your own. Module 5 is a very short module. We're moving to section 5.3, which is the module practice and quiz. What did you learn? You can read that on your own, but you learned about binary, you learned about hexadecimal, you learned a little bit about IP addresses. And then finally, down here at the end, we have the module quiz on number systems for Module 5, which you can do on your own. There were no packet tracers or no labs in Module 5. I may assign homework or two that has some number conversions and things like that. But watch for those to appear in Blackboard, and then watch for the Module 6 lecture to appear.